So you're welcome back to the channel, and now we are done with the basic part of Laplace transform. So we are going to be moving into the first shifting theorem over here. Now the first shifting theorem is when we have an exponential multiplied by a function of t. Like we have e raised to power at multiplied by multiplied by another function of time. So this it says that if we have e raised to power kt multiplied by f of t, that means it is equal to f of s minus a instead of f of s. That is provided that f of s is equal to the Laplace transform of f of t. So I'm going to be solving a question on this type of on the phase shifting theorem. So let's say we are asked to find for the Laplace transform. We are asked to find for the Laplace transform of e raised to power 2t times sine 3t. This way, the first thing that we need to do is to confirm the second part here that f of s is equal to the Laplace transform of f of t. So we need to look for our f of s first. So therefore, we have our f here. We can put it f of s is equal to the Laplace transform of sine 3t. Now we are going to be ignoring the e raised to power 2t for now. So first of all, after doing this, we are going to get Laplace transform of sine 3t is equal to 3 over s squared plus 3 squared, which is equal to 3 over s squared plus 9. So now that I've gotten the value of our f of s according to here, then wherever we see s, we are going to put s minus a, or rather s minus, we are going to put s minus k, that is given that e is equals to a raised power kt. So therefore our f of s minus k, and in this case our k is 2, right? So our f of s minus 2, our f of s minus 2 will be equals to 3 over, wherever you see s, you are going to put minus 2. So therefore, we are going to be having s minus 2 squared plus 9. You can simplify it as 3 over s squared minus 4s plus 4 plus 9. And this is equals to 3 over s squared minus 4s plus 13. So this will be our final answer on the first shifting theorem. And it's just simple. First of all, we just have to look for the normal Laplace transform for the function that is here. And then whenever it's multiplied by an exponential, we use the phase shifting theorem, and we just do s minus, wherever we see s, we do s minus whatever is the coefficient of t in the exponential over there. And we can actually prove it by putting two exponentials together, where we naturally, where we have the Laplace transform of any exponential. If we have the Laplace transform of, let's say, exponential 5t, we know that this is equals to 1 over s minus 5 in a normal sense. So we can break this down to prove this that this first shifting theorem is correct. So you see, we can break it into e raised power 2t times e raised power 3t. In this particular sense, we know that the law of indices, we have a raised power n times a raised power n is equals to a raised power n plus n. So I just did it the other way around so that I can break it down into something like this. Like this is literally equals to this. So I'm just trying to use it to prove that this first shifting theorem is correct. So let's say we have something like this, and let's use this as our main f of s. So we got our f of s as the Laplace transform of e raised power 3t, and this will give us 1 over s minus 3 normally. So then we do f of s minus the one that is initial, s minus 2, it will be equals to 1 over, whenever we see s, we put s minus 2. So we have s minus 2 into brackets, that is for this s, then we have our minus 3 over there, which is equals to 1 over s minus 2 minus 3, which is equals to 1 over s minus 5. So in some sense, we got the same answer as when we did the direct Laplace transform for this, and when we use the first shifting theorem to break it down. So it's just like a proof, and it does not necessarily, you do not necessarily have to break this down. It's just a proof to show that the first shifting theorem is correct. So that's how the first shifting theorem goes.